if the people over there can't see, if you could move over, I don't know, it's up to you, but yeah. Today will be, mainly programming, so we'll be actually implementing neural networks in Python. I think we had a question last time, like, would you rather use R or Python or whatever other language? R is good for statistical analysis, but for deep learning and stuff, I highly, it's not that good. However, there is a TensorFlow, they actually ported it to R, so you could use R, but I think the language is a bit cryptic, so I don't recommend using R. The majority, I think there was a survey about how much percentage of people use R and Python in data science. Survey. Kaggle did some sort of survey about it. So if you can check in the survey, it tells you. Also, as you can see, the current, in Australia, is it still free? Well. Yeah, this is a Kaggle survey. The median age for data science people is actually 34 in Australia. However, the world average is 30. So in Australia, people who are older tend to work with data. So, experience. So people who have 1 to 2 years experience, I'm assuming most of you guys, I'm guessing, will probably, the median age is actually 28, so I'm assuming most of you are younger than that. I don't know. Just assuming. In terms of employment, this is the employment data. So 60% is employed full-time, not employed but looking for work, so the unemployment rate is actually 14%, which is actually very interesting considering the Australian unemployment rate is actually 6%. So it's actually more than double. There might be a reason for that. So if you change, for example, data scientist, the unemployment rate is 0% for data scientists, right? So it depends actually on your job. So you can explore this data. Now where was I supposed to go to? I was supposed to, if you want to look at salary, I guess you can look at salary. Right, the median salary in Australia is $96,000. However, it depends on your experience. It depends on your experience, right? Pretend if you do less than a year. This is any. No, this is the total. Data scientist is 117,000. So it is changing. However, it depends also on your experience. For example, if your experience is 10 years, okay, they don't actually have data on that.
Remember that there's a bias in how people only fill out the survey if they want to.
No, that's true. But the world average is lower.
Like for example, the median salary in Australia is way lower than 96. I'm pretty sure.
Yeah, that's right. It's 78 or something. I don't remember clearly.
It's lower than that.
So Sydney is 78, but no, I'm just considering the other. But no, that's not what I was supposed to tell you about the Python and R thing. Where did it go? Oh no, about this one, which data, which tool they, which model they use first. As you can see, logistic regression or linear regression, 64% of people use it as their first model. Decision trees is next. Actually, neural networks is actually lower. It's not that popular because it's extremely hard to explain, and that's why people try to not use neural networks. So in terms of complexity, then logistic regression would probably be the easiest to explain. Now, where's the Python R thing? Oh yeah. Python is used by 76% of all data. Actually not data science. Let me check data science. Actually, I think data science is actually R's. Oh no, wait. This is data scientist. 86% actually data scientists, right? So the survey says that 86% approximately use Python and 70% use R. So some people use both. But as you can see, Python is the most popular currently. I think it beat R a few years, I think it was this year that it finally beat R. However, it says over here, statisticians use R more, right? R is more popular for statisticians. 91% of statisticians use R. But, yeah, where's the other one? Data, software engineers, yeah, they love Python, obviously. Yeah, yeah, that was just yeah. Anyways, program. Okay. So mainly this lesson will be about programming using Python. So we're using the NASA data for asteroids, so possible asteroid impacts of Earth. So these are all the asteroids which can possibly hit Earth. The system, so NASA collected this data using the Sentry system. I think Kepler, the space telescope, monitors like the route of the Earth, the asteroids and stuff. However, before I go into that, I want to explain some important stuff before. Probably move this a little. Okay, so this is important. Okay, so you guys have learned, so we learned the linear regression model, the perceptron Johnny was talking about, basic neural networks. We told you how in neural networks you can change the number of hidden layers, you can change the nodes and blah. So the question is, which of those architectures of the neural network is the most effective? For example, like this is a neural network, right? This is just linear regression with no hidden layers. This is one type of architecture. Another type of architecture could be like one hidden layer, right, like this. And then, this is another type of architecture. So the question is, which of these architectures provides the lowest cost, right? Which of these is the most effective in classifying something or regressing something? Would someone like to give me a suggestion on how do we find the best architecture? Like how many hidden layers, how many neurons, right, and nodes in the middle? Would someone like to suggest me a method of doing it?
I think it depends on data.
Yeah, so we already have the data. These are the inputs, right? And these are the outputs. So the aim is to which middle architecture is the best. How do I find that?
I mean, yeah, that depends on the data and what output we want to have. Like if data is just bunch of columns, then of course maybe the first one can be better. If data are some images, so second can be better. It depends on data.
So it depends.
Yeah.
So is there some
major
sort of
part depends on that, and then what actually we want to predict from that. That's also one of the things that affect which one is best.
Okay, so you're saying the data will affect the architecture. Okay, very good. So is there some sort of algorithm which determines how many hidden layers? Like, is it 2 hidden layers? 3, 4, 5, 6? How many, like 10 hidden layers? And each of the hidden layers, I can put like 100 neurons and then 200 neurons, 300. What is the method to determine which type of shape of the neural network is the best? So I want some sort of algorithm which can determine that. I don't want to like try myself. So that's the question. Would someone like to suggest a method to do that? How do I find the best neural network architecture? If you heard like Google, they already made a recurrent neural network to actually determine the best architecture in the middle. It's quite successful. However, assume that we don't have Google services. How do we do it by ourselves? How do we actually check which like is 4 layers good or is 3 layers good, or is it like 2 layers is good? Is 10 million neurons good? Like how do we actually determine which architecture is the best? That's the question. So obviously for each architecture we have a different loss, right? So we can use that. But how do we actually know which one is the best?
Maybe trying the train model on some unseen data and get the error, and then with the model which gives the less error, select that error.
Okay, but how many models do we have to try? That's the question. Let's just say the restraints are, we have 10 layers, right? In each of those layers, I can change 1,000 neurons, right? I can either put 0 neurons, 1 neuron, 2 neuron, 3 neuron, 4 neuron, 10, up to 1,000, right? So that means how many combinations? 10 layers times by 1,000, right? So how many is that? 10,000 configurations of your model, right? However, you can also change your activation function, right? You don't just have to use sigmoid, 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 sigmoid. You can choose this. You can either choose sigmoid, tanh, ReLU, or linear. So there's 4 choices. 10 layers plus 4 times 10 is 40, right? However, you also have your bias, which is what Johnny was talking about. Bias is, who cares about bias? Just don't worry about that. So how many configurations do you have to check? Approximately 10,000 configurations, right? Approximately 10,000. Who's going to wait that long? Who the hell wants to check 10,000?
Multiplied, not plus that stuff, and it will be more.
Sorry?
That 40 will be multiplied, I think, because then it will be 400,000 configurations.
Oh, what? Where?
This 40 thing should be
Yeah.
multiplied, right?
Yeah, multiply.
Not plus.
Oh no, this is the activation.
Yeah, so like for each configuration, if you have different activation in different layers, so it will be different, right?
Yeah, so but you have choice 1 is 4.
Yeah,
Oh, actually, it would be 5 actually.
It would be multiplied actually, not plus. That would be 400.
Oh yeah, yeah, okay, yeah, you're right. Okay, that's even worse then.
Yes.
Right? That means it's this, right? Well, that's horrifying, right? 400,000 checks. Yeah, you're right, sorry. Okay, so okay, pretend that each model takes 1 minute to train. So what's 400,000 times by 1 minute? 400,000 minutes. So I don't know how, like, what's 4? So 6,666 hours. Let's see how many days. 200. So 1 year nearly, right? So just 1 year, you train one model to find the best architecture. Who the hell is going to wait for 1 year, right? No one's going to do that. And then, well, you can parallelize your operations, right? If you have that's the whole point of multi-core computers. So maybe people don't actually know what's the point of a multi-core computer. Like Intel Core i7, it has four cores, right? What's the point of 4 cores? Well, then this is what happens. You divide your work into 4 pieces, and each core does each of the iterations. So you divide it into, yeah?
Could you potentially increase the number of neurons? And when the marginal increase of neurons actually over time, since time is the measure of loss?
That's a good point. So what you're trying to say is we develop some sort of cost function, and based on that, we optimize it so we can change the architecture. Is that what you're saying?
Mm-hmm.
Like if it's like 10 neurons, cost is 100. And then I'm going to assume that if I do 20 neurons and the cost is 80, I'm going to keep increasing the neurons.
Sure.
Unfortunately, that does not work. Remember, the neural network is a black box, right? So we don't actually know how to do that. That's the problem. Well, actually, there is methods to do it, like approximate it. But unfortunately, we don't actually know how to do that. Unless if someone makes some sort of method. And then, so remember, we're using gradient descent to find the weights, right? We can't actually use gradient descent to find an architecture. That's actually very complicated. But okay, so anyways, what I was trying to say was that if you check all the combinations, you will take 1 year, right? So would someone like to suggest me a faster way? That's the question. Is there a faster way, not waiting 1 year? Let's say that we can wait, let's do 4. Yeah, let's do 4. Let's say that we can wait 2 days. Can someone suggest me 2 days method? How do we actually find the approximate best? We don't want to be 100% best, but at least 99% is the best. How are we going to do that? What's the problem? Any suggestions? So okay, step 1 is this is brute forcing, right? Checking all the configurations to find the best one. Is there a smarter way? So you suggested a smarter way, right? The great updating. Let's just assume that we're not going to do that. It's too complicated. It's actually more complicated to formulate the cost function to optimize than actually doing the optimization. So another way, okay, so the method that I proposed before was called GridSearch. You probably heard of that if you did machine learning. GridSearch is finding all of the combinations of all of the neural network architectures and finding which one is the lowest cost. So GridSearch is good. 100% accuracy of finding the lowest cost. However, it is very slow. So another way is called Randomized Grid Search, if anyone's heard of that. So what is Randomized Grid Search? So remember, okay, this topic is actually extremely important because if you're trying to optimize a neural network, which is very large, you'll have to use some sort of these techniques. So okay, so the first method is called grid search, right? Pretend. So grid search is essentially doing this. If this was your landscape of all configurations, and this is your cost function, right? Some sort of cost function, right? What grid search does is it checks the first one, checks the second one, checks the third one, checks all of them, right? It checks all of them. But then this is a cost function. So would someone like to suggest me what's a better way of doing it? Like if this was cost. So clearly this area is very high cost, right? So why don't we just skip this area and just concentrate over here? So the question is, how do we actually know where to skip? Right? So what randomized grid search does is it essentially does not check every single combination, it just randomly checks. Okay? So step 1, I check here. Step 2, I check here. Step 3, it's literally random. Okay, so now the question is, okay, so I'm literally choosing random neural network configurations. Literally random. So the question is, why is random better than choosing brute force? Would someone like to suggest a method to tell me why randomly choosing is actually better than doing brute force? Why is random? So like I'm just choosing randomly, and then after like 10,000 iterations, after like 2 days I stop, and then I choose, oh, this one's the best, and then I return the result. Why is choosing randomly better than choosing brute force approach?
Because every model have the same probability of being picked and then being checked.
Good point, yeah? So you're saying, okay, so the probability will be, so would you like to formalize that? Like, explain it a bit more?
So it's like let's say we have 100 models, so each model have 1 by 100 probability of being picked and being checked, and then in that way it must touch some of the cost which is much lower, like that.
Yeah, okay, very good. Okay, so, very good. Okay, let's formalize that, and then I'll go directly, so a few more minutes. So the formalization of what you said was, okay, let's say that I have some sort of distribution of all of the configurations. Would someone like to tell me how much percentage of those distributions approximately are very good? Like, is it 1%? Is it 2% of those distributions? 3%, 4%? Would someone like to just give me a number? I don't know. Any? Or like, just guess. 1%? 5%? Okay, I would actually choose 0.01%. Well, actually, no, let's just do 0.1%. Okay, it doesn't really matter. You can choose any number. But I'm going to be extremely conservative. Okay? And I'm going to assume that only 0.01 of all the configurations are what we want. Right? So that means 0.99 is, so this is just 1%. 99% of all the configurations are bad. Right? So what is the probability of choosing a good configuration? What is the probability of choosing a good configuration? If I just choose one model, what's the probability of choosing a good one? So this is good and bad. What do you think?
Good. 0.01.
It's 0.01. Right? Because the probability distribution is 0. Yeah?
Wait, so if you randomly choose points, do you get that random, like that bell curve thing? That random, like, you know, where there's 57% in the middle and there's like...
Are you talking about the normal distribution?
Yeah, the normal distribution.
Depends.
Do you get some kind of...
That's
is it? Yeah.
That's not the same. So here we just kind of have like good models and bad models. So like instead of having kind of a curve of outcomes, you only have two. You have good and bad. So it'll just be like one column 99%, one column 1%.
Oh no, but I mean, like if you pick it randomly, do you get like a normal distribution?
Yeah, but what's your outcome? What's the value? Like from a normal distribution, you get the values like -3, 2, 17, -0.5. For this, you pick a point, you pick a model, it's either good or bad. So it's not quite the same area.
Well, I guess you could like just graph it and see for yourself. But yeah, but anyways, okay, so the probability of choosing a good model is 1%, right? So then, What is the probability of choosing a bad model? 0.99. Right, so the question is, how many bad models do I have? Okay, so the question is, how many good models do I have to choose, right? I have to like try until I get some sort of confidence. Okay, so let's say that I want a 99%, actually that's a bad number. Let's say that I want to be 95% sure that I get the lowest cost. Okay, so I only want 95% confidence. Right? If you want to increase it, that's up to you. If you want 100% confidence, then you have to do brute force. But let's just say that it's 95%. I only want 5% like leeway that I actually get a bad model. Right? So how do I actually, okay, so let's see. So do you guys understand that? Right? The probability of getting a good model is 1%. The probability of getting a bad model is 99%. And then my confidence is 95%. I want to be 95% sure that after some sort of number of iterations, I actually get the correct model. Yeah? Do you guys get that? Mm-hmm. Okay. So, how do we find the number of models or iterations? Right? So, what you do is remember, if you choose a bad model at the beginning, right? And if you try again, remember probabilities times on to each other, right? The probability of getting 3 bad models in a row is just the probability of bad cubed. Right? Mm-hmm. The probability of getting 3 bad models and then a good model is just the probability of bad cubed times the probability of good. Do you agree with that? Mm-hmm. Okay. So then, the probability of getting a bad model, right? I want to do that n times, right? I want to find this n. So n means how many choices I have to check, right? 1 minus it, because I only want the good ones. And this has to be greater than your confidence of 95%. Do you guys agree with that? Remember, n means how many times I have to get a bad model. 1 minus means, what 1 minus means is that, remember, all probabilities add to 1. So if you remove all the bad models, that only means I have left with the good models, right? And so this has to be larger than my confidence of 95%. Right, so how do I actually find n? So all you need to do is just solve it, right? The probability of bad to the power of n, right, is greater than 0.95 minus 1, right? And so this is just negative 0.05. If you cancel the minuses, if you cancel minuses on both sides, you do not swap the equality, that sign, right? If there's only 1 minus on one side, then you swap it. But because there's both, you don't need to swap, right? If you log both sides, if you log a power, remember you have to bring the power down. Right? And then you just divide by the log of the probability of bad. So, your number of iterations has to be larger than the log of 0.05 divided by the log of your probability of getting a bad model. I think I did some calculations before, but the number turns out, let's just try, log of 0.05 divided by the log. So the probability of getting a bad model is 0.99. So you only need to do 300 checks of all random configurations to get 95% confidence that you get the right model. Right? So instead of doing 400,000 checks, you only need to do 300 to get your final good model. Right? Do you kind of get the intuition behind it? So why is randomly choosing better? Because as you can see, we proved that you only need to do 300 to get a 95% chance of getting the correct model. Right? You don't need to choose all 400,000. You only need to randomly check 300. Right? Obviously, if you want to increase your confidence, like if you want it to be 99, right? 99.9% sure, then this number will go up to like 4,000 something or something, I can't remember, 10,000. But as you can see, this number is always smaller than 400,000. Yeah? So this is called randomized grid search. This is what most people will always use now. I forgot what's his name. I think it was, I don't know if it was Andre Carthy, I can't remember. Some sort of machine learning researcher, some very famous guy. He proposed the randomization method, I think it was a few years ago, and he proved that it's always better than brute forcing it. Just basic proof of, yeah. Yeah, any questions on that? So okay, so the point is why did I tell you all of this? When you do machine learning in industry and in real life, you will in fact have to check which model is the best. Like even if you have data, you don't actually know which model is the best, so you actually have to try all of them. But maybe there are smarter ways to try which model is the best. And so I propose for you to use randomized grid search. There are obviously other methods like Bayesian optimization, which is the closest to what you were saying, like gradient descent of the parameters. So yeah, Bayesian optimization can actually reduce this 300 even further to like 150 or something. But I won't discuss about that. Okay, so now programming. Okay, so so you have two choices: either to use Kaggle Online, or you can install Jupyter Notebooks. Remember, Jupyter Notebooks is yeah, but you have actually three choices, but I recommend you only to do the first two. Either use Kaggle Online, that's actually quite good, you don't need to install anything, or you can use Jupyter Notebooks, not this. Download, is there a download? Yeah, so this one, download Anaconda, it's quite big. But please download the Python 3.6 version if you're using downloading. If you don't want to, then you can use online Kaggle. So online Kaggle is online Python. You don't need to actually install anything. It's in your browser. So if you go to kaggle.com, this is not mine, but yeah, and you click, so this is, right, you click kernels, right, kernels, and then that thing kernel, oh wait, it's touchscreen, can I scroll? Oh, and you click new kernel, right, and you click notebook, right, if you don't know what I just did, I will repeat, right, you click kernels, you go to new kernel, and then you open notebook, right, you click notebook. Yeah, this is just the layout. Okay, I'll use the... So today we're going to use the NASA data, the asteroid impacts. So which asteroids are going to crash into Earth? So that's the data that we're using. It's publicly available. Okay, so since we're going to start from, I don't know like exactly what's the... So has anyone in this room actually played with Python before?
Yes,
Show of
yes,
hands, or
yes.
yeah, okay. Okay, so firstly, I think this is right. Don't worry about this now, I'm just trying because on your own computer it's a bit different. I think this box?
It's smaller.
Oh, is it lowercase? Oh, sorry. Oh, okay, it does work. Okay, so to read data in Python, we're going to use the Pandas package. So the Pandas is a, if you use R or something, it's just a data frame thing. So Pandas is to read tables and stuff. So in Python, to import the library, it's just import Pandas as PD. So people always ask like, what the hell does as PD actually mean? So you can just remove this if you want, right? Just import pandas, you can just do that. However, whenever you call a function in the pandas, you actually have to write this whole pandas dot something, right? Pandas dot la, right? When you call functions from the library, you actually have to do that, right? So people don't want to do that, right? You don't want to like continuously write pandas dot, pandas dot, pandas dot. So you change the name of the library to do as PD. So now instead of calling pandas dot, you can just do PD dot, which is the same thing as pandas dot. So it's just a renaming of the library within your environment. So also people ask like, why is it PD? Can it be something else? Yeah, you can do something else. You can do PA or something, up to you, right? However, the industry standard is actually PD. Most people understand what you mean by PD. If you use something else, probably people won't understand you. So use PD. Also, some other people asked, I think before, how when you do reading, like if you call some sort of function, why don't I just remove this and can I just call it like that? In fact, you can. You don't need to do PD dot. You can just call the function within the library, so just read CSV. You don't need to do PD dot read CSV. So okay, I forgot to tell you, like what does the dot mean? The dot just means you're calling a function within the library. So if you don't want to use PD dot, you can just do from pandas import star. Right? And star means everything. Import everything from the pandas without referencing anything. So now if you do that, I don't know if people know that one. It's actually, yeah. But you don't actually need to do PD dot anymore. You don't need to call the library. All of the functions are already inputted into Python. So now you can call anything, right? You read CSV, it's a function. Right? Before you had to do PD dot. Now you don't need PD dot. So I'm just going to do that. Okay, so it's much easier. Okay. Yeah?
I'm going to say it's not always best practice to just randomly import everything.
That's true.
Why might it not be best practice then?
Why might not make the best practice? Well, if you import everything, sometimes you have issues. Like for example, your function calls, the function names can override something. Also, memory usage will be a problem. But mainly it's because your functions can override another function. And yeah, memory usage. Is that okay? Yeah, those are the two main issues. But however, like if you're using one library, I highly doubt you're going to have any issue. So you should just do from, well, I'm not going to do from, yeah, that's not my main, this is what I normally do. Right, if you just want to copy what I do. But yeah, I don't do from pandas import that. But in R, when you do library something, you can import all the functions. So it's just R's, I'm just showing you like R's kind of power in Python as well. Okay, so the data is a CSV file, right? A CSV file, CSV stands for comma separated values. So it's just literally just commas in your text file. So it's just, right, comma separated file, I can't enlarge this, whatever. Right, a CSV is just like 1, 2, 3, it's just commas separating the data, something like that. Yeah, it's too small. But, so in Pandas, to import your data, you just write pd.readCSV, right? Read CSV just means I want to read a CSV file, so a comma separated values. And then you just type your directory, so wherever your file is. In your Jupyter notebooks, like if you install it on your computer, you don't actually have to do that. You can just type like, impacts.csv, right? But this is because this is in Kaggle, you actually have to do directory plus. So the directory, actually no, don't worry about directory. I just do this. That's the directory. In Kaggle, you have to do that, right? /input/impacts.csv. If you want to know what the dot means, the dot just means the beginning of your entire file system. If you do one dot means the current folder, right? If you do no dots, you do no dots, then it's like actually the folder within the folder. So it's just syntax. You have to use dot in this one because it means it's a file on the Kaggle server. But if you execute that, in execution in Kaggle is control enter, right? Hold control and then press enter and then you execute and then you see some sort of table on the bottom. See the object name, this is getting too small. Object name, period, start, all of this data, right? So when you call this function, so just one line, you read the CSV, you get some sort of this. If you get some sort of error, that probably means your file's wrong name, wrong directory, or something, right? So now we've read the data. Does anyone have any questions on that? Like any problems with that one, or should be fine? When you read the data, I don't want to keep reading the data, so I want to actually store it as a variable. I'm just going to call the data is equal to, right? So I stored the data, I stored the reading the data in a variable called data. And then you just do control enter, and then now the variable data has the data. It's stored in the data. I don't want to keep doing this, right? So I stored it inside data, and so this is your data. Can I minimize this top thing? Like, anyways, okay. Yeah, so do you understand the storing part? So you just store the core of the function inside data as a variable. You can use whatever function name, you can use asteroids or something, I don't know, it doesn't really matter. df, data, it doesn't really matter, up to you. Remember, control enter is execution in Jupyter Notebooks. So you have your data. Yeah?
You know that table looks nice to us, like it's really just a list with like some there's strings and floating numbers and everything. So even though it looks like it makes sense to us to the computer, it's just a big table, right?
Yes, correct. Yeah, so it floats strings, integers and stuff of this table. So okay, let's just see how it looks like then. So let's see all the data types. To see all the data types, there are multiple data types in Pandas. However, the main ones are integer. So integer is just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You also have negative integers. Well, they are integers. You also have floating point. So floating is decimals. 1.2, 1.4, 1.88888, pi, right? These are all floating. String is when it's a not a number. It's everything else. So if you do .d types, you have these things. So this is describing your data set. As you can see, object just means string. Object just means everything that is not a floating or an integer. Right, so as you can see, the majority is floating. There are some integers, there are other strings. Right? 64, if you're wondering what 64 means, like you probably understand what float int means, but what is a 64? 64 just means the length. So the actual, so if you know a 64-bit computer, it just means it can store in binary 2 to the 64, 2 to the power of 64. You probably can sometimes see float 32, or int 32, int 8. There are multiple data types. The whole point of using smaller data types, so if you reduce like to int 8, right, not int 64, is to save memory. It's a big problem when you analyze big data because you're using too much memory. Right, so that's .d types is just to check the data types. Right? You can also check the column names, and it's just .columns. These are the column names. So if you do .columns, they just give you all the columns. You can also describe your data set. Let's say that I want to find the mean, the mode, the maximum, the minimum of all the columns. In Pandas, it's just .describe. Right? You just do .describe, and then you have your, it summarizes all the data into some sort of table format. I think in R is the same. It has the count, the mean, the standard deviation, the minimum, the 25% quartile, and so on. Yeah, so this might be useful. However, if you didn't realize, this only has the numbered description, right? If it's not a number, how do you find the minimum? How do we find the mean of a string? Right, you can't do that. However, if you want to describe the data, which is okay, fine. I'll move on to the actual machine learning. That's a good point, I guess. Okay, possible impacts, let's just do it. Okay, I'll skip to actual machine learning. Okay, possible impacts. This is the column that we want to predict, right? These are the asteroids, right? The asteroid velocity, the asteroid magnitude, the asteroid diameter, the cumulative Paramo scale, I don't even know, whatever. But this is the column we probably want to predict. This is the possible impact, so some sort of number. Right? You can see if you do, you can call the column possible impacts. To call a column in Pandas, you do the square brackets and you put the column name inside, and when you call it, you can do that. So this is the column that we want to predict, right? So let's say, what's the mean of this column? Right, that's the mean. The mode is 1. The median is 6. Right? You can also do value counts. I think this is very important if you didn't see this before. This one counts all the numbers into bins, and it tells you, oh, 1 is a count of 130, 2 is a count of 74, and so on. This might be important. We want to predict the column called possible impacts, right? That's the thing that we want to predict. Okay, so we want to actually just drop it off from data, right? We don't actually want to show the machine learning model this column, right? We don't actually, if we show the machine learning that column, what's the point? So how do we drop the possible impacts off? In Python, it's just called pop, right? We want to pop it off from the data. And we name this variable called y. And once you do that, remember Control-Enter is to execute. Pop means to remove the column, but I want to store it somewhere else. Do not execute .pop again, because remember, it's already gone from the data. If you execute it again, there will be error. As you can see, the data has no more column, possible impacts, right? There's no more column which has possible impacts. That's what we want. So now my question is, do we need object name?
No.
What can we do with object name? Nothing, or I don't know, right? Probably object name is not a very useful thing. We don't need to use that. So let's delete that as well. In Python, you can also use the del command, which means delete. Delete. So I want to delete that dumb column. I don't need that, right? Object name. What is that going to do? I can't. That's probably not going to do anything. So del object delete name. Object name. Right. So now the data is no more object name. Right. No more object name. That's good. So what does period start and period end mean? What does that actually mean? So let's see. Okay, there's supposed to be a description of the data. Where is it? Impacts. Oh, what does it say? Well, okay, I'm assuming period start and period end means the probability, like what's the time period of an asteroid actually crashing into Earth. So, for example, the 5th asteroid can crash in Earth from 2017 to 2110. So that's just the range of when the asteroid is going to crash, right? So assume that, I don't know if we want to use that as a, what do you think? Should we use that within the model or should we not use that?
Maybe the range, we can build a new column with range stuff by subtracting end with start. that range can help us, but not exact the start and end.
Okay, so what you're saying is just to find the period end minus the period start. Yeah, that's a good idea. Let's do that. Range is equal to, right? When you want to make a new column in Pandas, it's just you just call the new column name, and this is just equal to period end, right? Minus period start. Control Enter, remember, means execute. Yeah. Okay, so let's see what range looks like. Looks something like that. This is years, right? Also, if you want to plot data, the plotting library is called matplotlib. You can use other libraries, but some people also ask, what does the percent sign matplotlib inline mean? It just means if you want to plot and you want to show it inside the notebook, then you can show it. That's all it means. This line just means I want to show the plots inside the computer. Right? So if you want to plot it, dot plot, dot histogram, I think, should work. Right? The majority of the years is very low, right? So approximately 1 to like 5 years or something. So that's very dangerous. Not good at all. There are some, okay, so good. We developed a range column. If we develop a range column, I don't think so we need a period start and period end. Let's just delete that. So delete period start. If you want to call multiple columns, I think you can do, you have to do this. If you want to call multiple columns, you can't just put 1 square brackets because it's ambiguous. You actually have to put 2 square brackets. Delete. Oh, okay, you can't do that. Well, that's sad. Well, you have to do it separately. Maybe, yeah, I think maybe Pandas should do that later. Probably recommend them to. Anyways, as you can see, that's the data now, right? We deleted those 2 columns, we don't need that. Right, this is your data. And our prediction we want to predict is y. Right, remember y is your asteroid impacts. What is the how many hits probably? Right, so actually I think this is a more okay, there are many columns you can actually choose. Cumulative impact probability. Maybe we should use that instead. There are actually, you can do multiple columns, I guess, you can predict. I think we have to delete that as well. Because this is actually the probability of a crash. Right, probability. I think we have to delete that. Otherwise we're giving the machine learning model too much of information. So let's just say that we want to predict the probability. Okay, so I don't know if, okay, let's just, okay, the first model that we're going to use is just linear regression. Well, actually, yeah, right, so the linear regression model is just a 0-layer neural network, right? And the package that we're going to use is just scikit-learn, right? So, right, scikit-learn is the package that we're going to use. Scikit-learn has multiple modules. The one that we're going to use is just linear model. Right, input, linear regression. Go. The from something, import something, just means I want to go inside the package, find wherever linear model the class is, I want to import that linear regression. It's just an easier way of like insert, you don't have to do this, import scikit-learn, right? And then you have to do scikit-learn dot linear model dot linear regression. No one's going to do that, right? This is much too complicated, and then you call the model. Instead, an easier way is just that. What? Oops. wrong. Yeah. Okay, so linear regression is the model that we're going to use, which is the zero-layer neural network with linear activation. And all we want to do is we want to fit, okay, so this is model, right? The first model that we're going to use is linear regression. So we call this, right, model, let's see what it looks like. It's copy x equals to true, fit intercept is equal to true. So the intercept is just a bias. Don't worry about the other ones. Normalize, you can talk about that later. But anyways, let's predict the probability of an asteroid crashing into Earth. So wait, let me just check the. Okay, so the majority of the asteroids have a very low probability of actually crashing into the Earth. The highest is 6%. That's still quite high. 6% is actually quite a large number, considering all the lower numbers are very small. So we want to actually classify these ones, right? We want to see if there's a high chance of getting those large ones. These are the problems. But anyways, let's see. Let's fit a model. Alright, so model in scikit-learn is just model.fit. Right? I want to fit the data to your probabilities. Oh, it's a categorical data. Did I not clean it properly? Oh, give me a second. Did I not? Oh, what? What is this? Why is this an object? Oh, interesting. So this data has some random, that column has like some strange thing, right? Which is a problem. Well, let's see what's the problem, right? To find what's the problem, we just do .value counts to see the description of the data. So as you can see, 3 of your data has that strange thingy. So how do we remove that? We have to delete that. So to delete that, all we do is just .replace. Actually, no, replace would be too complex.
I think we don't need this column because all values are 0.
Oh, that's a good point. That's actually a good point. Because all the values are 0, there's no point. Oh, yeah, let's just delete that.
Yeah.
Delete. Okay, so we delete that. Yeah, good point.
Can we use pop also?
Yeah, you can use pop, but what pop does is that you actually retain the deleted column. Delete actually means to delete. I don't want it anymore. Pop means you can keep it somewhere else.
But if you don't store the return value, you probably mean delete.
Yeah, that's correct. However, pop will actually show you the column. Like it will actually print out the column, which is very annoying. But yeah, you can use pop. I'll show you what I mean. Right, let's see. Let's say that I want to pop off asteroid magnitude. Right, let's see what happens. Control Enter. Right, it actually prints out this, which is quite annoying.
But you want the remain one.
Sorry?
You want the other column, you don't want the astronaut.
Yeah, correct. But I mean, I'm just saying if you use pop, you're allowed to. But I'm just saying it's annoying because you print all of this crap. So that's the only problem. There is actually a trick to not print all of that. Let me just execute everything else. I could have just, whatever. For example, this. Remember, if I press pop something, it will print out everything. If you don't want it to print, you just put a semicolon at the end. Right, this semicolon. If you do a semicolon, it won't print out anything. So you can use pop. It's up to you. Okay, so now let's fit the model. Model.fit. Your data is your x's, your y is your probabilities. So you fit your model. Right, so let's predict the original data. Actually, this is not a good practice, but whatever. So now this is your predictions. As you can see, there are negative probabilities. So obviously there is a problem with this because remember, we're predicting probabilities. We're not trying to do linear regression actually. But anyways, let's see what's the accuracy, right? So how do we find the mean squared error? Right. So the mean squared error formula is just y minus y hat. Remember the y hat means the prediction, right? Square it and then sum it all up. Right, that's the mean squared error.
By n.
Huh? Sorry.
By n.
Oh, yes. Divided by n. Technically, some people do 2, but don't worry. Yep, divided by n. However, we're not going to actually use that. We can just use the scikit-learn library from sklearn.metrics import mean. I think this is right. Squared error as MSE. Yeah, so scikit-learn already has a function to calculate mean squared error. So now you can just call it probabilities model.predict data. So the mean squared error is 6.12 times 10 to the minus 6. I don't know if that's good or bad. So we're not exactly sure if this is good or bad. So instead, what's the probability? Anyways, let's analyze. Where is the? I think this is correct. Yeah. Okay. So the coefficients of the linear regression model is you can just call model.coef. Yeah. So these are your coefficients of the model. So I want to store this as a data frame to make it much more easier to manipulate. So these are your coefficients.
So
I want to change all the column names to
yes, this is quite what
what's the time?
5 minutes.
Huh?
5 minutes.
5 minutes. Okay.
I
So these are the coefficients of your data set. If you do, I think I'm going a bit too fast. I was just showing you the. So as you can see, these are your coefficients, right? The asteroid velocity. The faster your asteroid velocity, you actually have a lower chance of actually crashing into Earth. The larger your asteroid magnitude and the larger your asteroid diameter, so the larger the asteroid, you actually have a higher chance of crashing into Earth. And the range, I guess, has no impact. It's nearly 0, so don't worry about that. The maximum, I don't actually know what those scales mean. But the main takeaway is that the faster the asteroid, most likely although there's probably no impact because it's actually quite a small number. The biggest impact is actually asteroid diameter. Well, don't worry about the scale. I don't actually know what it means, but diameter. The larger the asteroid, the higher the probability. It kind of makes sense. The larger the asteroid, you have a higher probability of crashing into the Earth. Yeah, okay, so that's a linear regression. So what happens if we want to use a one-layer neural network instead? So I was just going to demonstrate. I don't think we have time, but we use in Python we use the Keras library, which is a porting of TensorFlow. So to do that, or if you want to create a neural network, you just do from Keras import. From Keras models import sequential. Layers. Loading. Done. So this is building a neural network. So model is equal to sequential model.add dense. So dense means one layer. So that's the so let's say that we want to have 100 neurons at the front, right? I choose that, and you have to do input shape is equal to data.shape. I'm kind of like going a bit too fast. Data.shape 1. And then I want to do the activation function, right? The activation function is extremely important. The activation function that I'm going to use is just value. Oh no, oh wait, this is wrong. The output is only a 1, and I want the activation function to be sigmoid, right? What does a sigmoid do? Sigmoid is for probabilities, right? It squashes everything from 0 to 1, and that's what I want to predict. I want to predict the probability of an asteroid crashing to the Earth. So the activation function is sigmoid. I just chose really you can choose any. You can do tanh or whatever. Let's just choose tanh. You have to compile your model. I think it's lost. Let's just do. Actually, sigmoid. I think this is allowed. No. Oh yeah. Okay. Optimizer. The optimizer is your how do we actually do the gradient descent? The one that we're going to use is just Adam. The Adam optimizer. Don't worry about what it actually means. But stochastic gradient descent, you can also use stochastic gradient descent. However, we're going to use the Adam optimizer. The loss that we're going to use is mean squared error, so that's why I put loss is equal to mean squared error. And now we're just going to train the model. Model.train, data, probabilities, epochs, so the number of epochs, let's just do 100. Oh, sorry. I think it's fit. Training. And the mean squared error after 100 iterations is 7.99 times 10 to the power of 6. The linear regression model was a larger number, which means the neural network is actually better in predicting.
Linear was lesser than this.
Sorry?
Linear was lesser than this. Loss of linear regression model was lesser than this.
Yeah. Okay, so let's see. Let's see if we change the activation function.
Daniel?
Yeah.
No waiting.
Oh, the weighting. Okay. Well. Okay. Oh well. Yeah, I'll have to end that then. Yeah. I was gonna show you more, but later on then. Yeah. Thanks for coming.
I had to